to Zurich Instruments webinar on how to characterize magnetic materials using locking amplifiers. My name is Jelena Trbovic and I'm a product and applications manager at Zurich Instruments. And in today's webinar, I will be joined by Cryogenics, Yury Bugoslavsky, product manager there directly from London. Thank you, Yury, for joining. So to start off, let me give you a few words about Zurich Instruments. So we are a 13-year-old company. We produce locking amplifiers and arbitrary waveform generators and quantum computing control systems. We are about 100 people with various backgrounds and origins. Our headquarters are in Zurich, and we have offices in US, in China, in Japan, Korea, Italy, and France. And of course, we have partners around the world, for example, Taiwan and Australia. So in today's webinar, what we'd like to do is to show you the basic magnetization characterization techniques where locking amplifier, MFLI, and cryogenics VSM are used for characterization measurements. We have divided the webinar in 3 parts. In the first part, I will give you a couple of magnetization basics and also cover the locking amplifier measurement principle. And then Yury will move on and talk about VSM measurements, after which we will start with the first Q&A, where I really would like to encourage you to ask a lot of questions so we can clarify certain things in the presentation. After that, Yury will continue and talk about the AC susceptibility measurements, and we will have our final Q&A. Where we will address the rest of your questions. If we don't manage to cover all of them, we will publish a blog and write to you personally to address all these questions. So at Zurich Instruments, we have a large portfolio of locking amplifiers, and all of them can address a lot of the applications that pertain to magnetism, not just VSM and AC susceptibility. All these techniques vary from non-destructive to photonics to transport, nanomechanics, and we know that our community uses our devices, and they really help them boost their research. Another point that I wanted to make is that there are a lot of reasons to study magnetic materials. We use them in our everyday lives, in all the devices that we have. And in particular, in science, we're interested in scientific progress and to understand how the magnetic interactions appear and how they interplay with other physical phenomena. And for all of us, of course, it's important to have much better and faster devices, faster and denser memories, and spintronics devices that utilize novel antiferromagnetic materials for magnetic spin Hall effect and such. So when we start with a characterization process, what we do first, we start from the bulk material. Here you can see a big chunk of europium that one can take and put in the VSM system and measure its magnetization. We can check if there's any magnetic anisotropy by turning the magnetic field with respect to a certain axis. And then once we think that the device, that the material is clean, we can then evaporate and grow nice thin film structures that are then ready for further device preparation. After that, we can also play with multi-layers. We can see how their interactions can be used to change the device properties. When will they switch? What type of spin polarization we will have, and so on. And furthermore, we can also pattern small structures and study the dynamics of these such materials. Something that we saw in Martino Poggio's webinar, if you've seen it. And there is different dynamics that appears, and we can also look at that not just with VSM in mean field, but also we can look at it with some much faster methods. Furthermore, nanoparticles that are extremely interesting because their dynamics, of course, changes. They switch magnetization much faster, and they're also used in the medical in medical applications, for example, for magnetic hypothermia. And finally, I would like to mention molecular magnets, which exhibit tunneling magnetization, and they're also good candidates for qubits. Okay, so let's see a couple of measurements that then we start doing in order to understand the material's properties and see what the response is with respect to the external magnetic field. Over here, you can see the magnetic response as a function of external magnetic field, meaning that the induced magnetic moment in these systems will be opposite of the magnetization. We can also see paramagnetic, ferromagnetic, also anti-ferromagnetic and ferromagnetic, and all these things we need to distinguish clearly in our measurements to be able to say what kind of materials property we have. In addition to that, we also want to measure the magnetic susceptibility, especially as a function of temperature, to see the Curie-Weiss law and understand where are the critical points at which these materials lose or gain their magnetic properties, and we have the onset of spontaneous magnetization. So we can study magnetic phase transitions, we can study superconducting phase transitions, and also magnetic losses and complicated systems such as spin glasses. In this slide, what I'd like to just remind you that if we continue further sweeping back the magnetic field for ferromagnetic materials, we will see the hysteresis loop. And from this one loop, we can understand what is the switching field, what is the saturation magnetization, remnant magnetization. We can see if there is anisotropy with respect to the applied field. And we can really understand how we can manipulate this device. We can see the domain wall motion and see if we have multi-domain or perhaps single domain structure in this system. And all these, of course, is valid below the Curie temperature, where the spontaneous magnetic moments for ferromagnetic materials appear. And you can see that there is a wide range of these materials, cobalt iron down to europium oxide and europium sulfide, which we can study with all these techniques. So how does Locking Amplifier come into play? Well, it's very easy to study big magnetic signals, but if we want to reduce the dimensionality, if we want to study diluted magnetic semiconductors with very few impurities, we will have lots of non-magnetic or non-ferromagnetic or anti-ferromagnetic noise that we want to distinguish from our measured signal. And in that case, what we need to do, we need to look at the noise spectrum of the whole measurement system. And we will typically find the 1/f noise. We will also see the white noise. And what we want to do really is to try to be in the region where this noise is minimum. And of course, if we have the spikes and pickups, we need to make sure we avoid those. And the way to do that is to actually modulate the probe for the measurement system and avoid these noise spikes and go into the region where we can get a higher signal to noise ratio. And this is exactly where Locking Amplifier comes into play, because we can then modulate the signal coming into the system and read out the outcome, which is proportional to magnetization. And in a typical VSM system that Yury will talk about in greater detail. So this is done such that Locking Amplifier is providing the reference to the VSM rod where the sample is vibrating in the homogeneous magnetic field. And these vibrations induce the voltage in the pickup coil, which is also proportional to magnetization, and we can measure them differentially using the Locking Amplifier. So let's see how Locking Amplifier works. This is a quick reminder for those of you who have not worked with it yet. So locking amplifier measures the amplitude and the phase of the incoming signal that you want to measure, and it comes together with the noise, as we said. And what we want to do is measure its amplitude and phase with respect to a reference frequency. And the way this is done in locking amplifier is with the process called demodulation. So these two signals that come in, locking amplifier multiplies in a process called mixing. And then it projects these results. It projects these results in and out of phase of the reference frequency. And then when we're exactly at the reference frequency, we then have two terms in this product. We have this DC term that has amplitude and the phase in both parts, and we also have this time varying part, which is proportional to the 2 omega or two measurement frequencies. And this is something we want to get rid of, and we do this by using the low pass filters, and we are then left only with the X and Y components of these signals from which we can construct the amplitude and phase. And this is how locking works in a nutshell. And what's also important to know is that the low pass filters need to be set carefully. You can start off with the first order filter. It's a RC type of filter, and then you can stack a couple of additional filters on top of that if you're not happy as to how much noise your system is admitted. So you create a bandpass filter for your system. And you do this in a lock-in amplifier by choosing the appropriate time constant, which is inversely proportional to the bandwidth of the filter, which signifies the frequency where half of the signal power is admitted through the filter. So you can see here that if we increase the bandwidth of the filter, we have lots of noise admitted. This means that the time constant is very short. And further, if we continue reducing the bandwidth or increasing the time constant, we see less and less noise. However, the price that we have to pay because the time constant is getting longer is that we will also be measuring longer. And for this to be even more clear, we can look at how the filters that are necessary for these measurements are settled. We can see here that the first order filter takes about 5 time constants to settle or to reach the full signal amplitude. And if we have especially noisy system, we are basically forced to increase the number of filters in the demodulation chain, and we might end up having to wait about 10 time constants before the filter settles. And one way to see this is in this plotter, a little movie where we can look at the data, which are blue here, against these orange external parameter that we change, which you can understand as, let's say, magnetic fields that we need to sweep in the VSM measurements. And you see that for this 100 millisecond time constant, we need to wait more than 1 second for the signal to settle. So we need to be ready to perform these measurements. And as I said before, the lock-in amplifiers of Zurich Instruments are widely used in many magnetic applications. And what's important to note is that they don't only contain lock-in amplifier functionality, they also have scope capabilities, so you can see the noise spectra. Then we also have the plotter, as I just showed, where you can look at the data as a function of time. You can optimize signal to noise ratio. We also have the spectrum, parameter sweeper, and a number of options that you can use if you need more device functionality in your system. So this is where I hand over to Yury, that Yury tells us about VSM and MFLI in his measurement system. Thank you, Yury.
Hello, audience, and thank you, Jelena, for your introduction and very informative first part of the talk. I work at Cryogenic Limited. This company is based in London, and we produce superconducting magnets and a variety of low temperature equipment. Today, I'm going to tell you about two magnetic characterization techniques, vibrating sample magnetometer and AC magnetic susceptibility. All the illustrations, examples, and data I will show you were obtained using what we call a cryogenic measurement system. This is the machine shown in this photo. It comprises a general-purpose experimental platform, which gives researchers an opportunity to attain low temperatures and high magnetic fields and place the experiments in this environment. Such systems can be made with large magnets, which can generate up to 18 Tesla, and the temperature range we offer is between 1.5 Kelvin and 400 Kelvin as standard, with optional extensions at both the low temperature and high temperature ends. These magnetic techniques benefit greatly from a modern sensitive locking amplifier, the MFLI shown at the top. The invention of the vibrating sample magnetometer is credited to Simon Forner of MIT. And here you can see his first one-page note with the description of this apparatus published in 1956. The opening sentence, for those who can read it, says that this is a simple, versatile, and inexpensive device. This remains largely true today, and with the sprinkling of modern conveniences like superconducting magnets, sensitive electronics, and a few smart engineering solutions, the vibrating sample magnetometer remains arguably the most popular magnetic characterization technique. The simplicity of the VSM is largely due to the ease of sample preparation. The measurement is contactless, which means there is no need to solder or bond any electrodes to the sample. In fact, all you need to do is just to glue your sample to a light rigid stick. The sample holder shown here is a 10 centimeter long carbon fiber rod, and the sample is a small shiny ball we can just make out near the bottom end of the rod. When the sample is mounted, the sample holder is attached to the end of the vibrating shaft on the probe, like that. The probe is then moved into the load lock of the measurement system, and the sample is set to vibrate. I show a time lapse, not a time lapse, a slow motion video of the vibration. The actual process happens at around 20 Hertz, but you can see the amplitude and how regular the vibration is. After that, the probe is loaded into the system in its working position, and after a few clicks of a mouse, you can see the data coming up on your screen. A stationary magnetic sample creates a static magnetic field in the surrounding space. For spherical or elliptical sample with uniform magnetization, the external field is a pure dipole field as described by this formula. In most practical cases, the dipole approximation is also valid, and there is a unique relationship between the magnetic moment of the sample and the external field the sample generates. So by measuring the field, we measure the magnetic moment, and that's how the contactless measurement works. Coils are commonly used to detect magnetic fields. The voltage generated at the terminals of a coil is proportional to the time derivative of the magnetic flux through the coil. Therefore, to make our magnetometer work, it is necessary to set the dipole vibrating, like shown in this little animation. When the sample comes close to the coil, the flux through the coil increases, and vice versa. The schematic shown here is what is usually used in so-called longitudinal VSM, where the direction of the sample movement is parallel to the direction of the applied field. In this geometry, the best configuration contains two pickup coils. The coils are connected in such a way that they are sensitive only to the field generated to the moving sample. Other effects which may occur, for example, due to instability of the applied magnetic field, are greatly reduced and ideally cancelled. In the formula you see here, the Greek letter phi denotes the magnetic flux which crosses the coil. It changes as the coordinate of the sample changes. In the right-hand side, the function phi d is the flux produced by a unit dipole, and it describes all the geometrical parameters of the system: the size of the coil, the number of turns, the separation between the coils, and what's left is the magnetic moment m, the product of vibration frequency omega, amplitude a, and the harmonic term. So by detecting the amplitude of the voltage, we effectively measure the magnetic moment. One important consequence is that the sensitivity of the coil increases if the coil is smaller. So to make a very sensitive device, you would want to have the coil size as close to the sample size as practically possible. Now I will quickly go through the main hardware elements of the system. We start with the cryostat. This is a specially built vacuum vessel which allows us to keep the internal components at very low temperature. These days, most cryostats are cryogen-free, which means they use mechanical cryocoolers instead of expensive liquid helium. Inside the cryostat, we mount the superconducting magnet, usually a solenoid, wound with a special conductor able to carry very high current without dissipation. To be able to make meaningful measurements of our materials, we need to have the sample space with variable temperature, and so we add a variable temperature insert. For the VSM, we need an actuator or drive, which will produce regular mechanical vibration. The drive sits at room temperature on top of the system. That's it. And the sample is connected to the vibrator via a long, rigid rod. And the sample is placed in the center of the magnetic field. Moving on, there is a set of electronic units which control the operation of the system. First, we need units to do the basic housekeeping. There is a temperature controller and the magnet controller. The pickup coils are connected to the input of the locking amplifier, which is the best instrument for recovery of very small magnetic signals. Operation of the VSM is controlled by the digital function generator and data acquisition unit. This unit has several outputs which work synchronously. One of the outputs generates a regular signal with large amplitude, and this is sent to the reference input of the locking amplifier. The other input produces a sinusoidal current, which drives the vibrator motor. Inside the vibrator motor, there is a special device which directly measures the movement. The measured amplitude is sent back to the control unit for processing. And of course, on top of everything, there is a computer linked to all the instruments via the USB interface and running the control software, which performs various useful functions. Now that we have built our machine, we may ask, is it any good for any practical purpose? And what practical purpose there could be? Very often, interesting samples will have very small magnetic moments. These could be very thin magnetic films used in novel potential devices or recording media, nanoparticles, diluted magnetic semiconductors. So the sensitivity, which means the smallest magnetic moment the machine can detect, is one of the most crucial parameters which define its usability. A good way to understand the performance of the machine is to check whether the sensitivity can be improved by better design or engineering, or whether it is limited by some fundamental physics. If you think about the signal-to-noise ratio, the minimum detectable signal is determined by the amount of noise present in the detection circuit. The sensitive element here is a set of coils wound in thin copper wire. The coils have finite resistance, and therefore at a given temperature, they will generate Johnson noise due to thermal effect. Potentially, there could be other sources of noise, for example, intrinsic noise of the electronic measurement units, or noise associated with unwanted mechanical instabilities, vibrations, or instability of the magnetic field. Johnson noise results in voltage fluctuations on the terminals of a resistor. The root mean square value of the voltage fluctuations is given by this formula. Here we have Boltzmann constant, absolute temperature, resistance of the coil, and the bandwidth of the measurement. The bandwidth is determined by the measurement electronics, and in the locking, we're using two filters. The input bandpass filter is typically set to the 4th order or 24 decibel per octave. The output filter is usually conveniently set to 1 second time constant, which is good for our typical measurement frequency of 20 Hertz. It's a matter of mathematical derivation to show that with this combination of filters, the effective bandwidth is equal to 5/64 Hertz. Now, substituting the coil resistance, which is 2 kilo ohms, and room temperature into the formula, we arrive at the result. The fluctuating thermal voltage across the coil is equal to 1.7 nanovolts. Let's compare this to the sensitivity of the locking amplifier. The specification tells us that it is 2.4 nanovolt per root hertz, and root hertz is a convenient way of expressing the base sensitivity independently of the bandwidth. If you convert it to the noise we can measure using the settings I spoke about in the last slide, we get to 0.7 nanovolt RMS noise, and that is at 1 kilohertz measurement frequency. We measure at 20 hertz, and the spec is slightly less here, and we get 1.5 nanovolt per root hertz. If you compare it with the previous 1.7 nanovolt, we see that the coils we're using are very well matched to the input parameters of the machine we're using to detect the signal. Now, I'm going to be showing some magnetic measurements, and just briefly to tell you that it is convenient to use traditional magnetic units for the measurement. In SI, the standard unit is ampere times meter squared. In Gaussian units, we use EMU, and the relation is this: 1 EMU is 1 milliamp meter square. So these were the calculations, that's the theory. Now let's compare it with what we can get in practice using our machine. And the experiment we set up is by using a thin film sample. The magnetization curve for that sample is shown in this left graph. The sample is a small fragment of hard disk drive. So the recording medium is a ferromagnetic film. It is deposited on aluminum substrate. So the ferromagnetic film produces a small hysteresis loops here at the center, and aluminum is paramagnetic, so it gives us this constant slope at higher fields. To measure the noise, we simply zoom into the section of the curve at high field, calculate the statistical root mean square noise, and plot it as a function of temperature for a different set of curves, taken at different temperatures. What we get here is the plot on the right, which has a nice linear decrease of noise as the temperature decreases from 400 Kelvin to 100 Kelvin, and that's exactly what the Johnson noise should be behaving like. At 100 Kelvin, we hit the input limitation of our low noise preamplifier. But the overall result is that the machine is set up correctly, and it measures at the limit what is possible for our set of detection coils. This means that the combination of highly sensitive locking amplifier and various engineering devices we use to cancel noise result in the VSM, which is capable of measuring signals at 1 micro-MU level and lower across a wide temperature range. Talking about the high sensitivity of the locking amplifier, I would like to list a few essential points which make this electronic instrument so well applicable for magnetic characterization. The locking algorithm provides an excellent level of noise cancellation. The modern MFLI has a high clock rate of the input analog to digital converter and fast onboard data processing. It provides the option of a built-in fast Fourier transform, which is very convenient for us. And finally, there is a convenient software interface, which allows us to build various locking functions into our software package. To briefly conclude this part of the presentation, I would like to flick through several data examples to illustrate some aspects of the VSM performance and magnetic characterization. The simplest thing we can do is to measure Curie temperature of ferromagnets. So in this graph, we apply small magnetic field and ramp the temperature to see the Curie transition in nickel at around about 630 Kelvin and in iron at 1043 Kelvin. We can take a thin magnetic film and study its coercive force, which is important if you're working on magnetic recording media or magnetic sensors. We can study the reversal, the switching of the magnetic domains in the ferromagnet in more detail, but by employing the beautiful technique which is called first order reversal curves, which records partial hysteresis loops starting from different values of negative magnetic field. And here we usefully employ the automatic aspect of our machine, so we can run repeated measurements automatically, varying some parameters and producing a bunch of nice looking curves. And they can be processed further on to produce a colorful picture which describes the distribution of interaction fields and switching fields in this ferromagnet. The VSM is extremely useful for characterizing superconductors. And again, we are making very good use of the automation in this machine because we can set the temperature very precisely at very well-controlled steps, like this graph shows, stepping from 1.7 Kelvin to 3.7 Kelvin in 100 millikelvin steps, and producing a bunch of magnetization curves which allow us to determine the critical field and the critical temperature of indium. For practical type 2 superconductors, we can measure critical current density by contactless technique, which is also extremely helpful because it does not require making heavy-duty current contacts to the sample. And this brings me to the midpoint of my presentation, and we open the floor for questions.
Thanks so much, Yury. Thank you for this fantastic introduction and all the results you achieved with your VSM system. I have a couple of questions at this point. Keep them coming. So first question, what limits the measurement frequency, and can you go higher, and how high can you go in your measurement system?
Thank you. This question is to large extent a question of engineering. The vibrating drive we use has its certain mechanical characteristics, and we want to maximize the signal that we can obtain. The signal is proportional to the product of frequency and amplitude, and so we study the mechanical characteristic of the vibrator and find the sweet spot. There is another aspect to this question, and when we fine-tune the frequency, we need to find the frequency which falls between unwanted noise, which can appear in the Fourier transform of the raw signal. And there is always some noise associated either with the vibration of the machinery in the lab. There is a cryocooler which vibrates at 1.5 Hertz. So we simply want to avoid any interference from other pieces of equipment. And we can do it very efficiently because the MFLI, again, is a highly selective instrument.
Okay. Okay, thanks so much. I think I will answer one question that came from me when I discussed the lock-in measurements. So the question is, what did I mean by when that we will have less noise if we slow down the measurements. So by simply reducing the filter bandwidth, you increase the time constant, and then you need to wait certain time for the filter to settle. So the longer the time constant, the less noise you have. So these two go hand in hand. And on the other hand, if you reduce the time constant, you let more noise in, and you can do measurements faster. So and this is where you have to make some optimization also in the VSM system. You need to see how much of the noise you can tolerate, so you can speed up your measurement by reducing the time constant. Okay, so I think we will leave the rest.
Can I add just one sentence?
Sure. Mm-hmm.
Just on your last point, it is indeed to consider this time constant effect on the measurement. For example, when you choose the ramp rate of the magnetic field or the sweep rate of the temperature, you always need to keep in mind that the measurement can slightly lag behind your varying parameters. But there is a very simple experimental way to check that you are measuring correctly, which we can go into if there are further questions.
Mm-hmm. Okay, excellent, excellent. And you can also see in the lock-in plotter when the result actually settles and how much noise you have. I see a lot of questions coming in. Keep them coming. I think we should continue, Yury, with your presentation,
Mm-hmm.
and then we can leave the questions for later.
Okay, so moving on. AC magnetic susceptibility. I'll just quickly go through this set of formulae. If a small magnetic field is applied to the material, the magnetization is proportional to the field. And this coefficient, denoted by Greek letter chi, is called magnetic susceptibility. If the field is harmonic, it oscillates at a frequency omega. The magnetic response will also come at the same frequency, but generally the magnetization will lag behind the magnetic field, and this is a genuine effect, not the measurement effect, but it's a genuine physical property. Often the magnetic structure simply can't respond instantaneously to changing field, and so the response comes with some delay. Mathematically, this means that there is a phase shift between the magnetic field and magnetization. Alternatively, this result can be written as a sum of two components, like in this bottom line here. One component is proportional to cosine omega t, so this becomes what we call in phase with the magnetic field, and the sine component comes at 90-degree shift to the applied magnetic field. The coefficients in front of these terms, chi prime and chi double prime, are usually called real part of susceptibility and imaginary part of susceptibility for obvious mathematical reasons. In physics, of course, they both describe very real phenomena. The real part characterizes the strength of the magnetic response, while the imaginary is proportional to the energy dissipation which occurs in the sample during a cycle of the magnetic field. If now we consider that we are going to be using the locking amplifier to detect these effects, we noted that the first term in this formula maps onto the output of channel X of the locking, and the second term maps on channel Y. This makes the locking amplifier particularly useful and convenient instrument for simultaneously measuring both components of magnetic susceptibility. ACS presents a very useful complementary method to the VSM. It is particularly useful in studies of phase transitions, not least for the fact that the phase transitions are often marked by sharp peaks in susceptibility. So it's a very strong marker for your phase transition. And it is possible to make easy measurements using different frequencies in a wide range. This method also provides an insight into the dynamic effects in magnetic materials and superconductors as well. Here is a quick animation illustrating the basic principle of the AC measurement and how it's different from the VSM measurement. I'll switch this on, and you can see we are now applying a small magnetic field directed along the vertical axis, and the sample is now placed inside one of the pickup coils. The varying magnetic flux is created by the external magnetic field now, not by movement of the sample. In the absence of sample, the flux through both coils is equal in value, but given how the coils are connected, the two coils cancel each other, and the net signal from both coils is 0. The coils are therefore balanced. When the sample is placed inside one of the coils, it takes the coil out of balance, and the resulting signal is proportional to the susceptibility of the sample. The balanced pair of coils is a very sensitive device and can therefore be used for measuring small samples. Next slide, next slide. One particular example where this method produces beautiful and informative data. Sorry. Next slide is this, sorry. To make the VSM work as a AC susceptometer, we need to make a few additions to our electronic stack. We need to add high frequency function generator, which is connected to a small solenoid generating a high frequency field. The coil is still connected to the locking amplifier, but now because we are measuring at the frequency of the AC field, the reference signal is taken from the TTL output of the high frequency generator. The rest of the system remains essentially the same. We still have the same ability to vary DC magnetic field and temperature, but in addition, we now obtain a few new experimental parameters. We can vary the frequency of our measurement and the amplitude of the AC magnetic field, which in many cases adds valuable, useful new information. One particular example where this method produces beautiful and informative data is in studies of superconductors. The example I show here is the superconducting transition in titanium, which happens at the temperature of 550 millikelvin. To make this measurement, we combined a small AC susceptometer with our helium-3 refrigerator. You can see that at temperature below the superconducting transition, which is here, from 0.3 Kelvin to 0.5 Kelvin, the sample is perfectly diamagnetic. And for that reason, it has negative real part of AC susceptibility, shown here in the black curve. As we approach the transition, the real part of susceptibility drops sharply to 0. At the same time, the imaginary part shown is in red has this nice, sharp, pronounced peak, a strong marker of the phase transition. Unexpectedly, we see additional 2 smaller peaks, which indicate that our sample contains 2 other slightly different superconducting phases. Very good method for phase characterization of the material. Further, if we apply external DC magnetic field by switching on our superconducting magnet, and that is the picture on the left, we can see that the transition is pushed down to lower temperatures. And again, noting the position of these peaks in chi double prime, we can very conveniently build the phase diagram of the superconducting material. Another application of the AC measurement is in that it can be used for measuring electrical resistivity by means of convenient and contactless method. This is of particular importance when attaching contacts is difficult for one or another reason or impossible. So in this diagram, in this sketch, I show you a conductor, for simplicity, a cylinder, in applied axial high-frequency magnetic field. And when we apply the field, it penetrates into the sample through the surface by inducing surface circular currents. The currents screen the field, and the characteristic penetration depth of the field is given by this formula for skin depth, which shows us that the penetration depth is proportional to the square root of resistivity and inversely proportional to the square root of frequency and magnetic permeability. Looking at the formula, we can understand that at high frequency, the skin depth goes to 0. So effectively, the circular surface currents will screen the bulk of the material from the AC magnetic field. So as an illustration, here, I show you our measurement, which we made on a small copper sphere. Here we plot real and imaginary parts of susceptibility, but now not as function of temperature, but as a function of the excitation frequency, going from about 10 or 20 hertz to about 20 kilohertz. And we see here that the peak of the imaginary part now coincides with the point where the skin depth becomes equal to the radius of the sample. Now, using the formula, we can map the frequency of this peak to the conductivity. Repeating the same experiment at different temperatures gives us this nice set of curves. Here, the low temperature data has a peak on the left corresponding to low frequency, and as we increase the temperature, the peak shifts to higher F. Analyzing processing this data, taking the position of the peak and converting them into the resistivity, we get this graph, which is a perfect match to what we expect for the resistivity of copper. And this is my last example. To make a conclusion, I want to say that, echoing the quote by Simon Fauna at the top of the presentation, we can certainly say that magnetic characterization techniques based on VSM and AC susceptibility are versatile, and the cryogenic measurement system, this one, can be used for a variety of different measurements in a variety of experimental settings, fields, temperatures, frequencies, and so on. It is versatile. It is certainly sensitive, and the key part in the sensitivity of the machine is played by using modern, fast, highly sensitive piece of electronics. The system is fast compared to other high sensitivity systems. We can use relatively fast ramp rates of magnetic field and temperature and so on. The system benefits greatly from a high degree of automation. In the cryogen-free system, the variable temperature insert can run practically indefinitely, and you can program your measurement sequences to run as long as you need to collect your complete set of experimental data. And finally, the system is economical. It doesn't use expensive liquid cryogens. It is relatively low on maintenance, and with use of cryogen-free technology, the running costs are kept to the minimum. This is the end of my presentation, so I hand over back to Jelena. Thank you.
Thanks so much, Yury, for this really fantastic further examples from AC susceptibility measurements and all the things you've done and can achieve with your device. I'd just like to add a few words for those of you who would like to use MFLI in this system. If you don't have it, is that you can benefit greatly from it by you can improve the speed and sensitivity of your measurements. You can replace several pieces of equipment with just one box. You can also improve the resolution and accuracy. And you can also benefit from long-term stability of this device, which means that you can achieve better results faster. And in addition, because we have other options like multi-frequency, PID control and modulation option, you can do an impedance. You can do different types of measurements like AC susceptibility with multiple harmonics, transport and impedance measurements, which means that that you have single box for multiple measurements that you can do. So I really hope that you'll spend some time looking into this system. So now let's go to the final round of questions and answers. We received a lot of questions, which is great. Keep them coming so we can answer also later. I will take a look on my board. So I will mix a little bit and maybe start with a couple of clarification questions for you, Yury. First thing, what is the temperature range of your VTI? And also, if I may add, do you have to replace or have special low temperature, special high temperature inserts, and how does that work?
Thank you. The standard range, which you can achieve without any trouble or need to replace anything, is from 1.6 Kelvin at the low end to 400 Kelvin. So this is standard range, which applies to pretty much every probe we make. This can be extended to high temperature. The highest temperature which we can achieve corresponds to the example I showed. It's just above 1000 Kelvin for high temperature VSM. And we have a number of lower temperature probes, helium-3 for temperatures down to 300 millikelvin. And also we make dilution refrigerators of different specification to run at 100 millikelvin or 50 or 30 millikelvin.
I see. Okay. Thanks so much. Then next question for you, Yury, would be how to handle diamagnetic background from sample holder if you have a weak ferromagnetic signal. Can you give some tips there?
Yes, and the main tip is very simple if you think about it. If you recall the sample holder, do you mind, Jelena, if I show my screen again and go back a few slides?
Sure, go ahead.
I'll just show you one of the slides at the top of my presentation. Sorry, I'll just fast scroll back up. The most efficient way to cancel unwanted magnetic signals is to use a long and homogeneous sample holder. Because if you think about it, if you can see my mouse, the sample here will sit right in the middle between two pickup coils. There will be a pickup coil somewhere here above the sample and another one just below the sample. Now, if you make sure that the material of the sample holder is the same above and below, then the coils will not notice the movement of the holder. So the long story short, is that if you use a long sample holder and place the sample away from the end of it, whatever magnetic background of the sample holder may have will be cancelled. The other part of the question is how to cancel the signal which may be related to the unwanted vibrations, because we know that there is a cryocooler, there could be some other pieces of equipment in the lab which will send vibrations through the floor. And the answer to this is essentially choose your frequency of operation for the VSM wisely, find the sweet spot, and then the locking will do the rest for you.
Okay, fantastic. Yury, you can maybe stay on your slides. We have a question.
I'll stay on the slide.
About what is the method technique used to calculate critical current density from M versus H loop in type 2 superconductors? I think you showed this.
We could spend a long time talking about the details of it. I'll just put up the slide and tell you. We start with the case of simple geometry. So if your superconductor is a simple cylindrical rod, then you can derive a simple formula which relates the dimensions of the sample, the critical current density, and the width of the hysteresis loop, which I show here with this blue arrow. So the hysteresis loop here is what we record. If we start from 0, the center of symmetry of this graph, and the field here was taken down to negative, and then back up to maximum positive, and back to 0 to negative, and back to 0. So the superconductors always produce this nice looking characteristic diamond shape hysteresis loops. And the information about the critical current density is all contained in the width of the loop. There may be difficult mathematics to relate the experiment to the precise geometry of the sample if the geometry is complicated. But the field dependence of the critical current and temperature dependence of the critical current can be immediately obtained from a set of measurements like this.
Okay, I guess that can be a topic for personal discussion further with you, Yury. Thanks so much. I have a question that asked about the field intensity achieved with AC susceptometer and in which frequency range.
All right, so the frequency range is with our standard system, standard coil size is limited by 20 kilohertz. And the field, of course, because there is an impedance, inductive impedance of the coil, we can produce high fields and low frequencies and smaller fields and high frequencies. But the typical figure is that at 10 hertz, we achieve 1 millitesla field. So 10 hertz, 10 Gauss field.
Okay. Okay. Now I have a question about if you can say a few words comparing vibrating sample magnetometer and vibrating coil magnetometer methods. So what are the pros and cons, and which one is more accurate?
It's an alternative method, and I would say the way I see it, the vibrating coil is simply more complicated from the engineering point of view. The vibrating coil method will depend greatly on how homogeneous the magnetic field of your superconducting solenoid is. For VSM systems, we make higher spec homogeneity magnets. But still, if you imagine that you're moving the coil, it will inevitably sweep a little bit of the decay of the magnetic field of the solenoid. So it becomes more sensitive to unwanted signals. And that is the answer.
Mm-hmm. Okay. Okay, so the vibrating sample magnetometer is more is a better technical solution.
it's better technically, it's more feasible.
Mm-hmm. A couple more questions. Okay, maybe one more question for you, Yury, about room temperature measurements. How much of a drift do you get introduced? What are the problems you face, and how you mitigate them?
Or drifts, that is a great question. And in some instances, we did have to think long and fast how to avoid drifts or mitigate them, as you say. So for the VSM, the drift problem is not that important, I should say. The best technical device, the best technical way of mitigate the drifts is first to make sure that what we measure is a direct measurement of the sample environment. We have a thermometer which is very close to the sample. So whatever temperature drifts may occur far away from the sample do not affect our measurement. We have highly stable temperature control system. And we also have a device which measures the magnetic field independently. And that is very useful when we continuously run the magnetic field. So it's not a drift, it's a deliberate variation of the magnetic field, but we make sure that at every moment in time, we measure the momentary value of the magnetic field. The drifts become a lot more serious problem for AC susceptibility measurement. And we do have a rather smart method to cancel the drift by a hardware technique. It would take me rather long to explain the details. Let me just say that we know how to do it, and whoever in the audience is interested in the details, I will be happy to discuss this further.
Perfect, perfect, Yury. Thank you so much. I would just like to entertain one more question for me, after which I'd like to close. So one of you have asked actually, what is the difference between Zurich Instrument locking amplifiers that I showed, and for what type of measurements are they used? So you have locking amplifiers that work at different frequency range. From DC, they all work from DC to 500 kilohertz, 5 megahertz. Then we have HF2LI working to 50 megahertz, and UHF-LI to 600 megahertz. And you have different characterization methods. So for example, VSM is always done at low frequencies. And there are some AC susceptibility methods where the fundamental frequency is around 40 kilohertz. So you need to measure the higher harmonics deep in the high megahertz range. And this is where, for example, some of our customers use HF2LI. People also do MFM type of measurements. So you have scanning techniques and also optical techniques at higher frequency. So there's a lot there. I think we can continue this discussion. And Yury, unless you have something extra to add, I would like to invite all of you to contact both Yury and me with more of your great questions. We will to the addresses that we see on the screen, hopefully, and basically. You can come to us and connect, and we will also publish a blog where we will answer all these questions and make the summary of the webinar. Thank you so much for the awesome presentation, Yury. Thank all of you for coming and for spending your time. Challenge us, send us your measurement requirements, and we'll be happy to talk to you. Thank you so much, and hope to see you soon again in another webinar. Thank you.
Thank you, the audience, and thank you, Jelena, for organizing this very interesting event.
Thank you, Yury.
Thank you.